Today we're going to make these projectile from a height problems feel like routine, starting with probably the most common case that you'll see. And as I read out the problem, I'm going to map out a sketch. A ball rolls off a lab table with a horizontal speed of 8 meters per second, and the table itself is 19.6 meters tall. We're tasked to find two things. First, the time of flight, which is how long it takes before it hits the ground, and second, the horizontal distance it travels when it hits the ground. And here's what you have to know about these type of problems, is the time of flight has nothing to do with the horizontal speed. It is completely dependent on just the vertical motion. So what that means is it doesn't matter if your path looks like this, it doesn't matter if your ball rolls down like this, it doesn't matter if you drop straight down. The air time is the same for all of these situations. Now here's an important step, and I like to list out what we know before we solve. We know the table's height is 19.6. We know the horizontal speed is 8. And we know that gravity is a constant 9.8 meters per second squared. A bonus one is that initial vertical velocity is 0 because it's a straight horizontal launch. What about what we don't know? Well, we don't know time and we don't know the horizontal range, which is the distance. We're going to start by solving time because once we have time, we can very easily solve for the horizontal distance. And the formula we're going to use to solve for time is a standard kinematic equation with constant acceleration. It looks like this: y equals y0 plus vy0t plus 1 over 2 gt squared. Let me explain each part of this formula. Y refers to the final vertical position, which is the ground, aka 0. Y0 is initial position, which is the height of the table. This term here doesn't matter. Why? Because initial vertical velocity is 0, so this cancels out. And then simply 1 over 2 gravity times squared. Let's rearrange for time. Isolating time, you get this final equation. T equals 2h over g. Let's plug in our numbers. 2 times h. H is 19.6, the height of the table, divided by g, which is gravity, 9.8. Put this into a calculator, and it's equal to precisely 2 seconds. And that's our answer for t. Now, what about the second part of the problem, which is asking us to find the horizontal distance covered? This is simple. It's equal to the horizontal speed multiplied by the air time. Horizontal speed is 8 meters per second. The time we just found as 2, which means that we traveled 16 meters before hitting the ground. Basically, the height of the table decides the air time. The air time and the speed decides the landing point. Here's the second problem. A rock is launched 12 meters per second horizontally off a cliff. The cliff is 19.6 meters high. We have to find the speed on impact and the angle below the horizontal just before it hits the ground. What does that mean? Let's say our rock follows a path like this. The second it hits the ground, there is a velocity vector that looks something like this, representing its vertical motion and its horizontal motion, right? Now we're finding, 1, what is that velocity? And 2, what is the angle right here? I'll give you a second to pause and attempt this problem yourself before I walk you through it. Now, like usual, I'm gonna label out what we know. We know the height is 19.6. The horizontal velocity is 12. And again, gravity 9.8. What do we not know? We're looking for the angle and the final velocity. Here's my approach. Since we're looking for a vector, we're going to need both components of the vector, the vertical component and the x component. We already know the horizontal component, that being 12 meters per second. But the vertical component we have to find on our own. There's a formula that can help us find vertical velocity. It's this kinematic equation. And in the context of a vertical drop, we can write it like this. Vertical velocity equals initial vertical velocity plus gravity multiplied by time. This will give us the thing that we want, right? But we need time. So let me ask you something. What equation gives us time? We found it in the previous problem. T equals root 2 height over gravity. If we plug in our height value and our gravity number, we get 2 seconds because it's the same height as the previous problem. Let's plug in our values. So the final vertical speed is the initial vertical speed, which there is none, so that's 0, plus gravity, 9.8, plus time, which we just found here as 2 seconds. This means that your final vertical speed on impact is 19.6 meters per second. Let me make some space. So we now know everything to find the final velocity. To find the resultant vector's magnitude, the formula uses Pythagoras. So we know this side and this side, 19.6 and 12. The formula looks like this: the x component squared plus the y component squared, and that will give us our final velocity. We simply plug in our numbers, and the answer is roughly 23 meters per second. That's the final velocity right before we hit the ground. But what about the angle we hit it at? This is simple. There's a formula for it, and it's tangent of the angle equals the y component over the x component. Use the inverse tan function to isolate your angle. It's now this equation. And we know the y component and the x component. The y component was 19.6, the x component is 12. And your final answer for the angle is 58.7 degrees. These are our final answers. Next problem. A ball is thrown from a balcony that is 10 meters above the ground with a speed of 15 meters per second at 30 degrees above the horizontal. So above the horizontal is, imagine a horizontal line, and you go up and up and up and up until you reach 30 degrees. That is our launch vector. So you notice this is different to the previous problems. It's not just something rolling off in a straight line. And we have to find two things: the time of flight, so how long it's in the air, and then the horizontal range. Like always, let's list out what we know. The height is 10 meters. The initial velocity is 15 meters per second. And the launch angle is 30 degrees. Now we can break this initial velocity into its x and y components, with the x component being 15, which is the magnitude of the original vector, cosine of the angle, and that angle is 30. To find the y component, it's the exact same thing, but instead of cosine, we use sine. And of course, gravity, 9.8. Let me make some space before we solve. So, starting with the flight time. It's not going to be as simple as this formula which we were using previously. Why? Because now there's an angled launch involved. We're going to have to use a more complicated formula, and it's going to be the vertical displacement formula from kinematics. I'll explain why shortly. That is y equals initial y plus velocity multiplied by time minus 1 over 2 gravity times squared. Of course, final y is equal to 0. That's the ground level. Now let's plug our stuff into the rest of the equation, and then we're going to rearrange for time. The math is a little bit heavier here, so follow along closely. y0 refers to the starting point, that is the height of 10 meters, plus the initial vertical velocity, that is 15 sine 30, multiplied by time, which is unknown, minus 1 over 2 gravity times squared. All we've done is substitute in the numbers that we know. Now sine 30 is equal to 0.5, and half of 9.8 is 4.9. So we can go ahead and simplify our equation one step further. 0 equals 10 plus 7.5 t minus 4.9 t squared. This might look a little bit familiar because it's a quadratic. Let's move it around to make it into the standard quadratic form that you're probably familiar with, and I'm talking about this. Now let's rearrange this into standard quadratic form, which looks like this: negative 4.9 t squared plus 7.5 t plus 10 equals 0. I'm going to do a little personal habit of mine, and I'm going to multiply both sides by negative 1. Why? It just makes the equation look cleaner. It now becomes 4.9 t squared minus 7.5 t minus 10 equals 0. It's going to make solving slightly easier. So comparing this to the standard quadratic form, this is A, this is B, and that is C. It's a quadratic of t. So our quadratic formula will look like this. Let's plug in our values and find out what our time answer is. Negative b would be positive 7.5. b squared minus 4 times a, which is 4.9, times c, which is negative 10, divided by 2 multiplied by a, which is 4.9. So we just substituted in our values into the quadratic formula. And computing this answer actually gives you two roots. One of them is negative and one of them is positive. When it comes to time in physics and you get two roots and one of them is negative, one of them is positive, you always take the positive one, which in this case is roughly 2.39 seconds. Why? Because negative time does not exist. That is non-physical. We discard that answer completely. Now that we found time, we can find the horizontal range. So I'll quickly recap what we did because that was a little bit more complicated than the previous problems. We couldn't use the standard time formula, which is much more straight up, because this time there's a vertical component of velocity. And to consider that, we had to use a more complicated formula. We then rearranged for time, and then a quadratic appeared. We used the quadratic formula, and now we're here. The horizontal range is the easiest part of this problem. So this distance, again, horizontal speed multiplied by time. Horizontal speed is found here, 15 cosine 30, multiplied by the time, 2.39 seconds. Answer is 31 meters. So this problem was different because throwing it up like that instead of letting it roll off itself, it changes the air time. It means we're in the air for longer. And a longer air time means a longer horizontal distance covered. This is the fourth problem of this video. So from a platform that is 5 meters high, we launch a ball at 20 meters per second at an angle of 20 degrees. Here's where the problem gets fun. On our path, at the 28 meter mark, there's a fence that is 4.2 meters tall. Our question is, when we throw this ball, does it clear the fence? Does it go over the fence or does it hit it? Let's start with identifying what we're actually looking for in this problem. Well, we can find out whether or not the ball hits the fence by identifying the y value, so the vertical position, at x equals 28 meters. That's what we're looking for. And if this value y is greater than 4.2 meters, we cleared the fence. So this is the hardest part of this problem. So pay a bit more attention here. Because we're looking for vertical position, we can use the formula that we've been using for quite a few problems now. Y equals h plus vertical velocity, which I've written in component form, time minus 1 over 2 gt squared. Now here's the thing, we know everything. We know the height, we can easily find the vertical velocity, and we know gravity, but we're missing time. My strategy here is to just eliminate time. Finding time will make it very complicated. It's unnecessary solving. Let me show you how we can eliminate time from this equation. This is a bit more of an advanced technique when it comes to high school physics, but it's probably the ceiling of math that you're going to be seeing. So if you can follow this, you can handle anything. We have to start with listing out what we know. Height equals 5, velocity is 20, angle is 20. From velocity, we have the x component as 20 cosine 20, y component 20 sine 20. I'm doing this quickly because we've done this step a lot. And the final y position must be bigger than 4.2. Let's just find the bare minimum threshold, so equal to 4.2. And gravity is 9.8. That's every variable we know. And to eliminate time from this equation, we have to find a new equation that we can substitute in that only involves what we know, but is also equivalent to time. And the formula that does that job is the horizontal range formula. X equals the horizontal component of velocity multiplied by time. Rearranging for time, you get t equals x over horizontal velocity. Now what we've done is we created a time equation that we can simply substitute into this. You might be asking, why don't we just solve for time here? Again, it's unnecessary solving, so it would work, and then we can substitute the answer we get from this into here. But I like to do things symbolically with symbols, so we're gonna plug this straight into here. I've quickly written out what would happen if we substituted in our formula for time. It's the exact same equation. It just looks a little bit more complicated. But think about it like this. We know everything here. It's just a matter of simplifying the algebra now. which we can do. There's two ways you could go about this. The first way is brute force. So plug in every single value, chuck it all into a calculator, see what it spits out. Here's what I'm going to do. I'm going to simplify it a little bit for an easier equation. So this becomes h plus this, and we're going to expand this. So VO sine times x divided by V cosine. And this minus this big term, but expanded. And what that looks like is this, gx squared, let me make some space, divided by 2 initial velocity squared cosine squared. So what I did here is I just expanded the brackets. This and this are the same equation. We can go one step further. If you're familiar with your trig identities, then you'll realize sine over cosine is equal to tangent. So our final equation is y equals height plus tangent x, because these velocities cancel out, so we're just left with tangent x, minus this big thing here, so gx squared over all of this stuff. That is how we eliminate time and simplify an equation. All we have to do is plug in our things. So let's go ahead and do that. Now, the final y position is what we're looking for. The height is 5 meters. Tangent and the angle is 20 degrees. X is 28, because that's where the y position matters. That's what we're looking for. Minus this thing. So that would be 9.8 in place of g. X squared would be 28 squared, divided by 2, multiplied by initial velocity squared, which is 20 squared, cosine squared 20 degrees. This looks like a lot of stuff. We have done a lot of math, but now all we do is solve. You can put this into a calculator, and your answer is going to be 4.31 meters. So what this means is if you launch a ball 20 degrees up at 20 meters per second from a 5 meter platform, by the time it has traveled 28 meters in the forward direction, it will be 4.31 meters above the ground. So it does clear this 4.2 meter fence. Our ball just makes it by about 10 centimeters. A small change in speed and angle would matter a lot here. If you're a little bit slower, you probably wouldn't make it. Next problem. You're a height of 10 meters and you're shooting a projectile at 20 meters per second. You want it to land exactly 30 meters away, right here. You have to find the best angle to launch it at to make this happen. I'll give you a chance to pause the video and try and solve it by yourself. And I'll give you a clue. There's some heavy algebra in this problem with quadratics. Now I'll solve it on screen. So we want the angle. And because time is not asked directly and is also not necessary, we're going to do the same thing we did last time and eliminate it. Let's list out what we know. Height equals 10 meters. Distance equals 30 meters, because that is the desired horizontal range. Initial velocity is always 20 meters per second because it's a fixed speed. And gravity, 9.8. Let's make some space and start the heavy solving process. I'll tell you all about my approach. First, we're going to select the formula. It's the same thing as last time. Y position equals height plus all of this stuff. We've seen this before. We used it in the last problem. All we have to do is eliminate time with the same technique. And that formula, if you remember correctly, last time was x over horizontal speed, right? But this time, instead of x, we're going to use our d value, because that is our horizontal distance variable this time. Same thing, but we need to keep the labels consistent. And this is specifically initial velocity. Let's plug this in place of these t's here. And our equation is 0 equals height plus VO sine theta, and then d over VO cosine minus 1 over 2 g d over VO cosine squared. Same equation as last time. Don't panic if there's a lot of symbols on the screen right now. Again, it's just a matter of simplifying it now. So from trig identities, we know that sine over cosine is equal to tangent, which means that we can expand this portion of the equation like this, cancel out the velocities, and it becomes tangent distance. What about this complicated part? It's going to look the same as last time, which is g d squared over 2 initial velocity squared cosine squared. Here's something special that we can do. By the way, I'll quickly write out the rest of the equation. This is tying in with trig identities again, and trig identities is probably the hardest math that you're going to be seeing in high school. But I want to test you for this. If you look at this equation, 1 over cosine squared is actually equal to 1 plus tangent squared. That's a trig identity. And by the way, if you're unfamiliar with that, it's like these sets of equations that equal each other. They're helpful for simplifying equations. That means that we can write this equation as 0 equals h plus tangent, which I'll just represent with t from now on, d minus g d squared over 2 velocity squared, and our new thing, 1 plus tangent squared. Let me recap what we've done. I've replaced tangent with the letter t, it's just easier to read. And we took out the cosine from the denominator and turned it into this term here using trigonometry. I understand the math is getting pretty heavy, but the physics big picture takeaway is simple. We're solving for tangent because tangent involves the angle, right? That's our end goal. And it's going to end up being complicated math. It's going to be quadratics because we have multiple angles that could work, theoretically. And the math is going to tell us all about it. Now from here, we're in a good position to start treating this like a quadratic. Think back to the standard form quadratics, which is this. This would be a coefficient. And we're going to call this coefficient capital C. We're just going to go ahead and solve for the numerical value. So 9.8 multiplied by d squared. D is 30. Divided by 2 times initial velocity squared, which is 20 squared. That's equal to 11.025. So that's our capital C value here. Why did I do that? It just makes our equation and final solve process a bit easier. So we can go and write that here. Let's plug in the rest of our values as well. Height is 10 meters plus distance, which is 30 meters times time, minus C, which is 11.025, 1 plus t squared. If you notice, it's starting to look like a quadratic. Go ahead and expand this term here. You get 11.025 minus 11.025 t squared. And if you move stuff around in the equation, just do some general cleaning up, combining like terms, you get this. 0 equals negative 11.025 t squared, which is that, plus 30t minus 1.025. And we're going to multiply both sides by -1 again, like I did earlier in the video. It's a personal habit of mine, and it just makes things a bit cleaner. So the real final equation, 0 equals 11.025 t squared minus 30t plus 1.025. That is our quadratic. And we are now ready to put it into the quadratic formula to solve for our angle. If you're still following the algebra, that's impressive. And this is what's going to set you apart when it comes to solving problems. If you can solve this, you can solve any problem that's easier than this when it comes to projectiles being launched from a certain height. So in quadratic terms, this is A, this is B, and that is C. Putting it into the formula, and I'll do this quickly, 30 plus or minus 4 times A times C divided by 2A, which is 2 times 11.205. That's a quadratic formula. I just plugged in our values straight away. Now, if you compute this with a calculator, you get two answers. T1 equals 2.69. And the second answer you get, T2, is 0.0346. Again, if you remember, T represents 10. So we can write it like this, 2.69. or 0.0346. Guess what? All we have to do now is use the inverse tan function to solve for the actual angular value. And the final angles are 69.6 degrees and 1.98 degrees respectively. Let me recap what we just did because that was a lot to follow. Created an equation through a lot of substitution, quadratics, and simplifying to find tangent. And then, because tangent involves the angle, all we had to do was isolate the angle, use these final values, and we find the two possible launch angles that gets our projectile to land at 30 meters away if we launch it at a certain speed. These two angles both work. So usually in projectiles like this, you have a high throw angle and you have a shallow throw angle. Both are valid. Next problem, and this one's actually really fun. So ball is fired horizontally at 14 meters per second. The cliff it was launched off is 19.6 meters high. The car on the ground, which we'll draw as a rectangle, moves directly away from the cliff at 6 meters per second. Here's a question. How far ahead of the cliff should the car start at the instant of the launch so that the ball will land in the car? This sounds complicated, and it is, but it's also extremely satisfying if we're able to solve it. We're looking for the head start that the car needs so that by the time the ball hits the ground, their movements have synced up. So before we start solving, I'll give you some intuition. Because the car is moving much slower than this ball, the ball is going to cover more forward distance than the car, which means that the car needs a head start. At the bare minimum, it needs a head start. That's what I'm saying. Otherwise, the car cannot catch the ball. So what are we looking for exactly? We're looking for the head start it needs, and we're going to call this length of distance L. That's the car's initial lead distance. Let's list out what we know. So height is 19.6. That's the height of the cliff. Horizontal speed of the ball is 14. Horizontal speed of the car, which we'll call VC, standing for car, is 6. Again, gravity 9.8. Let's make some space and I'll show you how we solve this step by step, and it's gonna click in your mind. You're gonna understand it. First, as we learned earlier in the video, the horizontal distance covered, it depends not just on the horizontal speed, but also the air time of your projectile. So let's find time. And because it's a pure horizontal launch, we can go back to using our simple, easy formula. Let's plug in our values here. 2 times height, which is 19.6, divided by 9.8 gravity, gives us precisely 2 seconds. This is an extremely valuable variable for us. So let's write it down here. Now we have to do some equation setting up, and this is a valuable skill to have if you want to be really good at physics, and if you want to ace your exams at this level. So we want the horizontal distances to match up, right? So basically the horizontal distance of the ball, which is Vxt, it should be equal to the horizontal position of the car. It should be the same spot on the axis. Now we can easily find the horizontal distance covered by the ball. But what about the car? When it comes to the horizontal distance covered by the car in the same time frame, then the formula would be the speed of the car multiplied by time, similar to this one. But because it has a head start, we have to consider that as well. So we're going to add in L amount of meters. So our equation looks like this. Vxt equals Vct plus L. What are we looking for? Of course, we're looking for L, right? We're looking for the head start it needs. And this is going to be really satisfying. Let's isolate L and we get this equation, Vxt minus Vct. Let's factor out T to give us an easier equation. To get L equals T Vx minus Vc. And plugging in our values, time is 2 seconds. The horizontal speed of the ball is 14 minus the speed of the car being 6. This gives us 2 times 8, which is 16 meters. That is our answer for L. What does that mean? If L is 16 meters, that means the car has to start 16 meters away from the base of the cliff. So it has a 16 meter head start. By the time the ball hits the ground, it has covered 28 meters of distance horizontally. In the same amount of time, which is 2 seconds, the car will only cover 12 meters. And our math is correct. the head start of 16 meters, we'll place our car at the same position as the ball so that our car can catch it perfectly. This type of problem is extremely satisfying. All we did was set up some math and use variables. And now it's time for the final problem of today, and also the hardest problem. If you've made it this far, that's some impressive focus. Let's finish it out strong. So just for fun, if you want to pause and try this yourself, give it a go. But I'm going to walk through it myself now. So from a height of 20 meters, you need to land a distance at least 30 meters away on level ground. What is the minimum launch speed needed? And what angle makes it possible? We're looking for two things. First of all, of course, the minimum initial launch velocity. We're also looking for the angle that we have to launch it at. This is harder than any previous problem because we're only given two things, the height and the distance. So this is going to resemble past problems. We're going to use an equation that has tangent to find the angle. That helps us. And for a minimum velocity, that will probably pop up somewhere in our solving process. But we're going to find the angle first. So as a statement of what we're trying to find, we want the smallest initial velocity for some angle theta, which makes the projectile land at distance d, which is 30. We also know the height is 20. And gravity, like always, 9.8. Let's select the formula, and we're going to use the exact same formula as, I think it was problem 5. And this formula was the formula where we eliminated time. H plus d times tangent minus g d squared over 2 initial velocity squared 1 plus tangent squared equals 0. This is the exact same formula we used in problem 5, but we were writing tangent as t and we wrote this term here as c. We're going to do the same thing. So it becomes h plus dt minus c 1 plus t squared equals 0. If you expand this and then simplify the equation, you can write it in a much more clean quadratic form. And it ends up being ct squared minus dt plus bracket c minus h bracket equals 0. I skipped the algebra because it's something that we've done before. But before we continue with the solving process, let me tell you two things. One, remember we're solving for the angle, aka this tangent. And two, I have to explain to you something called the discriminant. If you look at the quadratic formula, the piece that is under the square root, which looks like this, is the discriminant. The discriminant is represented with delta, so the triangle symbol. And the discriminant tells you something about the answer of the quadratic. If your discriminant is equal to 0, it has one real root, so one real answer that we can use. If it's bigger than 0, it has 2. And if it is in the negatives, so sub-0, then there is no real answer for us to use. And it starts to get involved with complex numbers. Now, the discriminant is important here. Why? Since this is a quadratic of t, our quadratic formula will give us answers as to what t is numerically, which gives us the angle. And because we're looking for the minimum launch speed and we want a real angle, then the discriminant cannot be below 0. Otherwise, we don't get a real angle and everything breaks. So it must be greater than or equal to 0. That is our boundary. Let's just say equal to 0. That's the threshold. That will give us the minimum velocity for a real angle. It might sound a little bit complicated, but we're going to see it play out in the math. So the discriminant has to be 0, right? And the discriminant is b squared minus 4ac from the quadratic formula. B squared in this case would be distance squared minus 4 times a, which in a quadratic form would be this coefficient. So c. I know it's a little confusing. A is c, whatever. And finally c, which is the constant at the end of the quadratic, which in this case is this, c minus h. That is our discriminant, and it must be equal to 0. Otherwise, our answer is not valid. Now, why am I showing this? If we can solve this here, we can find minimum velocity. Why? Remember what c represents. C represents g d squared over 2, and here's a key, velocity squared, the initial velocity. So let's solve for c. And we can do that with some simple rearrangement. If we open up these brackets and do some moving around, we get 0 equals c squared minus hc minus d squared over 4. All we did was rearrange some stuff. You can do it yourself, but we've done this before, so let's be efficient. This is a quadratic in C. So let's put it into the formula. C equals negative B, which would be positive H, plus or minus root. And then this would be B squared, aka H squared, minus 4AC. A is 1, the coefficient of the first term. C is this entire thing here. 4 times AC squared is simply D squared. Do you see this? We cancelled the 4. So that would be our term here, D squared, divided by 2A in the quadratic formula, which would be 2 times 1 or just 2. This is our quadratic formula to find C. Remember why we're finding C, we can find minimum velocity with it. Stay focused here, because we're almost there. Because we're looking for velocity, let us write in the actual value of C. And what we're going to do is we're going to rearrange for velocity squared. I'll show you how we can do that. It just looks like there's a lot going on, but it's actually a simple rearrangement. We can cancel the 2's. That makes our job easier. And then we're going to multiply velocity squared onto the other side. And then we divide this big term onto the left. Try and visualize the pieces moving around. I don't want to have to write all of it out. I think that would bore you. But we basically just juggle them around and we end up with velocity squared equals GD squared divided by this, which is H plus H squared plus D squared under a square root. And yes, it's actually plus, but I wrote plus minus before. Now, we're actually ready to solve. There's a square left. We can square root this whole thing. But at this point, any further cleaning up is just up to you. And I'm going to do that. So our final formula is this. And we're going to insert our numbers as we write it. G is 9.8. D squared would be 30 squared divided by H, which is 20 meters, plus square root height squared, 20 meters squared, distance squared, which is 30 meters squared. And put this all into a calculator, solve all of it. Your final answer for the minimum velocity is 12.5 meters per second, somewhere around that. But we're not done. This is the hardest part complete. We found the minimum launch velocity so that we can land 30 degrees away. But what is the launch angle? You might say, oh, well, we can find the launch angle with this formula, which we used earlier. And this would be easy, right? We just have to find the components of our velocity and plug it in here. But what happens when you try and find the components? Initial velocity, which is 12.5. Let's say the x component, so cosine. Oh, but we need the angle. So that's not an option. So I'll give you a second way. Look back in your notes, all the way back when we wrote out this equation, which is the quadratic in tangent, represented with t. T, if we went and solved for it with a quadratic formula at this stage, right here, before doing all the discriminant stuff, you would find that t is actually equal to d over 2c. And the discriminant is 0, so this is our only answer. Let's plug in our values. So 30 for d, 2, and then, oh, but we need c. Don't worry, because we can find c very easily. We just have to plug in more stuff. I know there's a lot of substituting, but we're nearly there. Plug in 12.5 and everything else. C comes out to be something like 36.055. Plug that in here, and you find that tangent, which is t, is equal to 0.535. Use the inverse tan function. You find the final angle is 28.1 degrees. That is the minimum launch speed and the angle at which you should launch it at to hit a perfect target 30 meters away from a platform 20 meters high. We just solved it. There was a lot of quadratics. If you follow the math, that is incredible. And finally, before we finish the video, I want to let you know of an opportunity. I'm doing something I've never done before, and I'm opening up 5 private spots where you can get unlimited help from me for 30 days straight. You can ask literally anything, any time of day, as much as you want for 30 days. If you're interested, it's called Inner Orbit. Go check it out in the description. It's not going to be here forever. There's 5 seats maximum. Fill out the application on the website. And if you're a good fit, I'll email you within 12 hours.